Hi everyone, this is Yong Wen. Today is June 17th, 2020. In today's video, I gonna briefly go through the research item, the progress of them in the past week. So from the June 11th to June 17th, 2020, you can see here's the highlights of the Gantt diagram. There are two items in my to-do list, and for the past week, I spent a month of time on learning the new tools or new technology we're gonna use in the research. For example, like the CUDA, like the JNI, I spent a lot of time on them. So I did make very big progress on the first item, but I think I did indeed make some progress on the second item. So we can look into the details. So for this week, I only want to go through the deep learning workflow. So as we discussed in the last time, we are adopting the second design, which we are going to implement the GPU deep learning workflow for the research purpose. And we discussed we can use the method, all the techniques such as a CUDA, such as a JNI directly to interact with the GPU and try to call the code from the Java. And for example, we have the CUDA C++ and CUDA C, and then we can call the code from the Java. So I spend a amount of time learning the CUDA. I also take a class from Udemy. I think that is a very good class. And I finished maybe 25% sorry, the 35% about the class already. I think that's really helped me to get the idea how the GPU works and how the CUDA works. So I will go through some programs today, briefly go through some example today. So firstly, maybe let me pull up the CUDA program. And CUDA, either we can use a CUDA C or CUDA C++. And currently the tutorial is a kind of mixture of the C and C++. And you can see from the code, for example, maybe I can go through one of them. For example, we can go through not this one. Let's comment this out. And let's go through the sum array. I think this is quite representative, and I can quickly go through the code on how it works for interact with the CUDA. So here is, you can see basically it's written in C, but there are some header files that's written in C++. You can see if we include this stdio, which is in turnout we are using a C, and we use a printf in main place. And basically for the CUDA code there are two parts, and one part is a host side code, the other part is a device side code, because we are interacting with two physically separate codes. Some of them are running on the GPU, some of them are running on the CPU, and the code on the CPU we call them the host code, and the code on the GPU we call them the device code. So you can see that the CUDA device defines some mediators, for example like the global, and we can define some CUDA code. For example, here we have several inputs. This is a method that will be called in the kernel, and basically the inputs is several pointers, and then we can define the size. And what we need to do is to do the add function for this array, maybe two arrays, and then we return that array to the CPU, and that is purpose. And then we also have a summary array method which is working on the CPU. Why we need this is because we want to have a validity check, because we don't want them to be wrong. For example, if we have only very small amount of summation, it will be very easy to print out the result, right? But if there are more than 10,000, how can we validate that the accuracy based on we check the printout? That's not available. And so we just compare the result between the CPU version and the GPU version, and to output if that is correct. So basically in the main method, this is quite simple. You can see in the C code we have the malloc, we have to allocate the space for the array we need. For example, we have two pointer that is for the array address. We allocate the byte size, which is 10,000, I believe, somewhere. So maybe it's defined later. So basically, firstly, we allocate the space for the CPU, and then we initialize the two arrays, randomly initialized. And then we do memset because we want to assign the value to these two arrays. And then we do the summation in CPU because we want to have a ground truth first. And then we launch a kernel. Basically, for the kernel, we have to allocate the space as well, and we have the cuDA-malloc. This is quite similar to C, but the difference is we have to give a pointer to pointer as the first arguments, and which is DA is a device pointer. The DA, DB, DC is 3 pointers. It's respectively point to the 2 arrays as input and 1 array as output, and these all have to be allocated space in the GPU and with the same size as the CPU. So what we do is we copy from the CPU to the GPU, the 2 arrays copy from CPU to GPU, and then we call the kernel. So you can see we allocate the block and the grid. This 2 is basically the grid represent how many blocks or thread blocks in a grid we have. It can be 3-dimensional, can be defined in a DIME3 type variable. Basically have 3 x, y, z, but for this example, we only have 1 dimension. And for the block, it also a 3-dimensional variable and represents that how many threads per block. And so actually we have 4 arguments can be put into the kernel, but right now we are only using 2. And you can see we are put 3 pointer on the device and into this as argument into this kernel. And then we also put the size. And then we do a CUDA device synchronize because we want to have the host wait until the device finish the work. Otherwise, the host does not need to wait because it's synchronized call. The host can directly do something else. So we also have a GPU check, and this is a method in the macro in the header file. We want to check the runtime error because there are 2 types of errors normally. One is a runtime, one is a compile time error. The second one is quite easy to check because that's syntactical error. Many editor or many IDE can help you to pick out those errors easily. But for the runtime, we have to check, for example, like the divide by 0 or the memory overflow or something like that. So those unexpected things we have to check during the execution. And finally, after we've done that, and we also do the memory copy back from the device to host. And you can notice that we do many clocks here, because we want to compare the clock time, the running time between the CPU and GPU, do the comparison as well. For the GPU, we separate into 3 parts. The first part is copy from the host to the device, and second part is the kernel running time, and third part is from the device to the host. So there are 3 parts can be summed together as the GPU runtime. So you can see that we will print out the amount. And finally, we will free the space. Basically, we'll free the pointer either on the GPU and on the CPU. So if we run this execution, you can see I think we initialize 10,000. So let me see. Okay, so it's 2 to the 25 size of the data. So it's quite a very large array because we want to compare the time. But actually, you can see from the result, the GPU is running slower than the CPU, but the execution time on the GPU is actually very fast. But a lot of time is taken from from the transfer time, we need to copy the data from GPU and to the GPU. So that takes a lot of time. But later, we will see a lot of other computations the GPU will take very big advantage over the CPU. So this is one part I'm working on. And so let's get back to the slides. And second part, the GNI, I also spent some time to learn the GNI because I'm not familiar with that as well. So I also made some dummy program and to make the GNI work as a kind of hello world dummy GNI. So for this example, you can see that basically I write a Java code, and which is basically have a static load library that load the hello DLL file. So basically right now maybe this file is not existing, but when we call Java this file, and we will, by that time we will have that DLL file. But at this moment we just define the method or the operation we will do. So firstly we load this hello.dll, and then we define a native method called the say hello, and basically the say hello is from this hello.dll file, and then we call this say hello method. This is very simple from the Java code, and then next thing to do is we will compile this Java code with a little bit different way. We use a Java C-H, and which will output two files, and first one is a class file normally we will have, and second one is a H file. This is a header file, and which will give us a name of the class of this Java code. So this class is what we will use in the C code. So you can see I copy the class name, and then I implement the body with a printf. So this is basically a C code. I implement the printf hello world. That's very easy. And then next thing to do is to compile the C code. And I spend some time to configure the environment. For example, I use I believe I use a Syncwin to install the GCC, and then I compile the code using this code line, because we have to include the GNI, and GNI I think we need to include two headers from the GNI. So I specify the repository of them, and then to use them to compile the C code. So after the compilation, we will get the hello.dll file. Then we can call this hello.gni.java by just call the Java hello.gni. Then I can get the result. So this is a very dummy example how we call the GNI from Java. I also tried to call that from the Eclipse, but that's not successfully yet. I think I will spend some time later to make that work. But I think it's very good. I think it's always very good time when learning something new, and it's very exciting. I also make a lot of notes about CUDA, as well as GNI. I hope I can wrap them up soon, and also to delve deeper and deeper and make something new and very exciting to make the deep learning workflow useful for some user in the future. So I think that's pretty much for today's video, and I hope to catch up sometime later with the second item. The first item, the extending the survey to the general version. I haven't spent too much time because I mainly focus on the learning process in the past week, and I hope to have some more idea about the research direction. But I will come back to this item very soon, and hopefully we can get back to the normal track soon. So thank you so much for your time. Until next time, happy coding.